Saturn is big. It's a gas giant with an average radius about 9 times that of Earth, making it the second biggest planet in our solar system. I say average radius because its equatorial and polar radii differ by almost 10%. It's 60,000 kilometers at the equator compared to 54,000 kilometers from pole to pole. With an average density of around 0.7 grams per centimeter cubed, it is only 1/8 the average density of Earth. However, because its volume is so large, Saturn's mass is over 95 Earths. This low density makes Saturn the lightest planet per cubic centimeter by far, and it's the only planet of the solar system that is less dense than water, about 30% less. So if you had a bath toy of Saturn that shares the same density as the planet, it would float. This is because Saturn is 96% hydrogen, which is the lightest of the elements. However, average density doesn't tell the full picture of what a planet is like. Saturn is classified as a gas giant because what we see of the planet is simply gas. It doesn't have a rocky surface under the cloud layer. However, Saturn is most certainly not gaseous all the way through. It's got too much mass for that. You see, the further into Saturn you go, the higher the pressure builds. Eventually, the pressure becomes so great that the hydrogen stops behaving like a gas and starts acting like a liquid. So, in a way, under Saturn's atmosphere is a liquid hydrogen ocean. Even further below that, it may be that there is a metallic hydrogen layer, where the pressure is so great that hydrogen starts acting like a metal. And beneath that could be a metallic and rocky core. We do know that Saturn has a very hot interior, reaching 11,700 degrees Celsius at the core. This is twice as hot as the surface of the Sun. If we look at Saturn through the infrared, we can see Saturn's glow, represented in brilliant shades of electric blue, sapphire, and mint green. On the night side, where there is no sunlight, Saturn's own thermal radiation lights things up. This light is generated deep within Saturn, and it works its way upward, eventually escaping into space. In fact, this infrared image reveals that Saturn radiates 2.5 times more energy into space than it receives from the Sun. You may not have noticed, but Saturn's atmosphere has a banded pattern similar to Jupiter's. If you increase the contrast when you look at images of Saturn, this becomes more apparent. Saturn's bands are much less chaotic than Jupiter's, however, and are much wider near the equator. And ever wondered why Saturn is yellow? It's believed to be due to ammonia crystals in the upper atmosphere. But while the atmosphere of Saturn may appear calm, the planet is actually extremely active. The winds on Saturn are the second fastest among the solar system's planets after Neptune. They can be a blistering 1,800 kilometers per hour. Visible storms are also known to appear on Saturn, like this one that lasted just under a year in 2011. It had been the pattern that every 30 or so Earth years, the planet produces what is called a great white spot, which is a unique but short-lived phenomenon believed to occur once every Saturnian year. However, we have spotted a few of them over the last 30 years. If it does follow a 30-year pattern though, we can expect another one any time now. Sadly, even if it does happen, we will only be able to see it through the Hubble Space Telescope, as the Cassini mission ended a few years back. Saturn has plenty of smaller storms too, where lightning is often produced. Cassini has even detected the sound of thunder. While this might sound weak, the sound you are hearing is actually the radio waves produced by the lightning converted to audio. In reality, lightning on Saturn is about 1,000 times more powerful than what we see on Earth. Still talking about storms, but moving on to the planet's poles, we find that each pole has giant, permanent storms. NASA reported in November 2006 that Cassini had observed a hurricane-like storm locked to the South Pole that had a clearly defined eye wall. Eye wall clouds had not previously been seen on any planet other than Earth. The ring is similar to the eye wall of a hurricane, but much larger. The clear air in the center is warm like the eye of a hurricane, but on Saturn it is locked to the pole, whereas a hurricane on Earth drifts around. The North Pole is even more unusual. There is a persistent hexagon-shaped storm that rotates with the planet, not with the atmosphere. The straight sides of the polar hexagon are each about 13,800 kilometers long, making them larger than the diameter of the Earth. Why does this happen, and to such a large scale? Well, we don't really know. However, the speed differential and the viscosity parameters between atmospheric bands here are likely to be within certain margins to allow such an unusual polygon to form. Lab tests have since been done where polygons could form in a circular tank of liquid, rotated at different speeds at its center and near the outer boundary, so this is the leading theory at the moment. Interestingly, towards the center of this hexagon, another eye wall can be found. While not anywhere near as strong as Jupiter's, Saturn does have a magnetosphere, potentially generated in the metallic hydrogen layer of the planet. It is large, extending far beyond the planet, and it is strong enough to deflect solar wind from the Sun. And much like other planets with magnetospheres, Saturn has auroras. Their location and brightness strongly depend on the solar wind pressure. The auroras become brighter and move closer to the poles when the solar wind pressure increases. The same process produces auroras on both Earth and Saturn, where electrons from the solar wind stream along the magnetic field lines directed into the upper atmosphere. There, they collide with atoms and molecules, exciting them to higher energies. The atoms and molecules release this added energy by radiating light at different colors and wavelengths. On Earth, this light is mostly from oxygen atoms and nitrogen molecules. On Saturn, it is from hydrogen. The rings for me are one of the highlights of the planet. Saturn has a prominent ring system that consists of 10 continuous main rings. While they are mainly named after letters of the alphabet, the naming conventions are a little confusing, so bear with me. The first 5 rings, from the closest to the planet outward, are the D ring, which is very faint, the C ring, B ring, which is the brightest and widest of all the rings, A ring, which is the last of the large bright rings, and then the F ring. The rings extend from 66,000 kilometers to 140,000 kilometers above Saturn's center, and are made up mostly of water ice, with small amounts of dust and rocks. If we look in the ultraviolet at a section of the brightest rings, it shows there is more ice towards the outer part of the rings than in the inner part. The red in the image indicates sparser ringlets, likely made of dirty and possibly smaller particles than in the icier turquoise ringlets. If we look at a picture representing radio occultation, we can judge the size of the individual particles that make up the rings. Color is used to represent information about ring particle sizes based on the measured effects of 3 radio signals. Shades of red show regions where particles are larger than 5 centimeters in diameter, green shows particles smaller than 5 centimeters, and blues show particles less than 1 centimeter in size. Overall, it's thought that particles in the rings aren't bigger than 10 meters, and most are microscopic in size. The main rings are thought to be as little as 10 meters thick to 1 kilometer thick. We can see that the rings are not perfectly symmetrical. During the planet's equinox, the rings can get a bit wonky. Look at the top of this video where the B ring meets the A ring. Zooming in on the structure reveals ridges and spokes a couple of kilometers tall, their presence given away by their shadows. Zooming out again, we can see the scale of how many spokes there are during this period. Oscillations happen all the time in the rings though, perhaps due to the presence of a shepherd moon, or even just naturally. The differences, which can be seen all in only a day, can be up to 200 kilometers. So I've talked about the D, C, B and A rings and also mentioned the F ring. The F ring can also get quite wonky and has a perfect example of what is called a shepherd moon. It's called Prometheus, and it leaves a beautiful ripple in the F ring as it orbits. Once during its 14.7-hour orbit of Saturn, Prometheus, which is only 102 kilometers across, reaches the point in its elliptical path where it is farthest away from Saturn and closest to the F ring. At this point, Prometheus's gravity is just strong enough to draw a streamer of material out of the core region of the F ring, and that's what causes these ripples. So, what comes after the F ring? Well, this is where it gets confusing. First, you have the Janus or Epimetheus ring, the G ring, Palleni ring, and then the E ring. I find this picture amazing, as these rings are much more visible being backlit by the sun. This bright blue ring is the E ring, and you can just about see the faint Palleni ring at the top of this picture. The G ring is the next distinct ring, and again you can just about see the Janus or Epimetheus ring at the top below it. And can you see us? We are all in this picture too. Here's Earth and the Moon. The very last ring is the newly discovered Phoebe ring, a huge yet dispersed ring that extends far beyond Saturn. It's so large that if it were visible from Earth, its apparent diameter would be the size of 2 full moons across. It probably originated from Saturn's 200-kilometer wide moon Phoebe, which had been battered in its past. Phoebe orbits just outside of the ring, and probably keeps this dust contained from going outward. On the other hand, it is also suspected that dust in this ring is falling inward, eventually falling into Iapetus, Saturn's outermost regular moon. It has a bizarre combination of colors because dust from the Phoebe ring settles on it, but because Iapetus is tidally locked, only one side of the moon ever faces Saturn, with the backside of it exposed to the Phoebe ring, meaning its two faces look very different. So now you know about the rings. I think you'll agree that they are so interesting in their own right. Theories abound as to why they are there, but we simply don't know. We know that some of the moons are responsible for some of the material there, and we also know that some of the material there is responsible for some of the moons. And talking of moons, Saturn has at least 82 of them. They come in all shapes and sizes, and most uniquely, Saturn's largest moon, Titan, which is even bigger than Mercury, is the only moon in the solar system with a thick atmosphere around it, which I have done a separate video about here. I'm also going to throw in here that Saturn has the Death Star orbiting it, biding its time. We call it Mimas. Generally though, most of Saturn's moons are very small, only a few kilometers across. Lastly, I'm going to talk about Saturn's orbit. Saturn orbits about 9 to 10 times further away from the Sun than Earth does, and 1 year on Saturn takes 30 Earth years. Funnily enough, a day on Saturn is different depending on where you are situated. At the equator or at the poles, a day lasts about 10 hours and 14 minutes. Everywhere else on Saturn, a day lasts 10 hours and 38 minutes. The issue is, because Saturn isn't solid, it's not bound to rotate at the same speed all over. I just want to leave you with this. Few sights in the solar system are more strikingly beautiful than softly hued Saturn embraced by the shadow of its rings. The gas planet's subtle northward gradation from gold to azure is a striking visual effect that scientists don't fully understand. Current thinking says that it may be related to seasonal influences, tied to the cold temperatures in the winter hemisphere, and despite all that we have learned from Cassini, Saturn remains a world of mystery.